Okay, so today's video is gonna be on the connection between zeta and primes. So we won't be talking for a long time today, hopefully. We're gonna be discussing first of all the definition of zeta, its immediate connection to prime numbers through an Euler product, and then we're gonna discuss some functions that connect to primes, such as the pi of x function that counts the number of primes up to x, the mu function, the Möbius function, and some others. And this will involve a discussion on the logarithm of zeta, the logarithmic derivative of zeta, and stuff like that. So we're gonna begin with the definition, I guess. So let's begin with that. So let me remind you. So here's a definition. So the hope is that by the end of this video, you're gonna get a glimpse of this connection between zeta and prime numbers. But we're gonna be talking more about this when we get to the prime number theorem and other theorems of this kind. Okay, so for complex numbers, s equals to sigma plus it. So this is the standard notation. Sigma is the real of s and t is the imaginary of s. We're gonna define zeta of s to be the sum of 1 over n to the s as n runs from 1 to infinity, and this is gonna be defined for sigma bigger than 1. And this assumption here is of course needed because we need to have absolute convergence of this object we're working with. So let's note that with this assumption, zeta of s is bounded by 1 over n to the sigma, and by basic calculus this is finite for sigma bigger than 1. Okay, so this is the definition on the right half plane. So we define zeta on the half plane to the right of 1. Over here we define it in this way. Okay, so at the first glance, if you look at this, it looks like it has nothing to do with the primes. What on earth does it have to do with primes? Like it's the simplest looking series you can sum, just summing like 1 over n to the s. What does it have to do with primes? So here's the first thing we're gonna show. So I guess let's call it a proposition, maybe a theorem. So what we have is that we have the following. So we can express zeta in an Euler product 1 minus p to the minus s to the minus 1 as we run over the primes. So we can express it as a product over the primes of these factors for sigma bigger than 1. Okay, so hold on, what's going on here? So to see this, I'm gonna be sketching the proof of this. So let me sketch the proof. So here's a sketch of the proof. Okay, so how do we see such a thing? So we need to make an observation. Let's make the following observation. Let's observe the following. Let's see what happens to finitely many factors if we multiply finitely many of these. So if we look at the product up to let's say big P of primes less than big P of 1 minus p to the minus s to the minus 1, the first observation is that p to the minus s, which is p to the minus sigma, is less than 1. So the inner factors are actually geometric series, and they can be rewritten as sums, of course, so they can be rewritten as, so this is p less than or equal to big P, 1 plus p to the minus s plus p to the minus 2s plus dot dot dot, because it's a geometric series. And then the point here is that you can see we have the fundamental theorem of arithmetic, right? What does it say? It says that if you look at like a tuple of this form of integers, of natural numbers, and you can map every number like that to an integer n that is the product with these exponents. So you can map integers that are so we can take these to be bigger than or equal to 0. You can map these to this integer n, and this map over here, it's actually a bijection. It's a bijection between the exponent vectors to the integers. So here we have the set of exponents, and here we have integers with let's say whose prime divisors are less than or equal to p. Okay, so we have this bijection here, and by the theory of sums of products and products of sums, you can interchange these by absolute convergence. And the point is, once you do this interchange and use the fact that we have this bijection by the fundamental theorem of arithmetic, you can see easily that this product must be, this finite product must be the sum of 1 over n to the s as n runs from 1 to infinity, such that whenever p divides n, we must have that p is less than or equal to big P. So to summarize what we've done here, we started with this finite product, and we've shown that it must be equal to this sum. Okay, this is important for us because it immediately gives what we want. And why is that? Well, because if you look now at the difference between zeta, so if you now look at zeta of s minus the product p less than or equal to p of 1 minus p to the minus s to the minus 1, this, if you use the fact that this product, which is the same as this, equals this, you can, and you use the fact that zeta is the sum over 1 over n to the s, then you can upper bound this difference by the sum over n bigger than big P of 1 over n to the sigma. And remember here we have sigma is bigger than 1. So as p goes to infinity, this thing goes to 0, because it's the tail of a convergent series. So what we've shown is that this product in the limit, it tends to this thing. So this is one way to see it. Of course, there are different ways to see it, but mainly it's like the analytic version of the fundamental theorem of arithmetic that allows you to express zeta as a product like this. Okay, so this is the first encounter with primes. Like starting with zeta, you end up with something in terms of the primes. Okay, cool. You might think, who cares? Well, the first observation here is that this representation is important, that it has an immediate consequence that's not so apparent at the beginning. So the first consequence of this, so as an immediate consequence of this, or a corollary, we know that zeta is not equal to 0 for sigma bigger than 1. So if you know a little bit about zeta, you know that the zeros of zeta are of a big deal. we have the Riemann hypothesis conjectured about the zeros of zeta that we're going to come to later. But the point here is that we immediately see, just from this Euler product representation, and by the way, this product is called an Euler product. So from this Euler product representation, we immediately see that zeta cannot have a zero in this right half plane. So over here, it cannot have any zero. And why is that? If you know a little bit of complex analysis, that's immediate. It's because this product is absolutely convergent. And for an absolutely convergent product, it equals zero if and only if one of the factors is zero, but none of these factors is zero for the real of s bigger than 1. So zeta cannot be zero. So if you know the theory of products in complex analysis, that's great. You see it immediately. But let me show you a rather elementary way to see this. So a quick way to see this is that if you look at the product over all primes less than or equal to p times zeta. So if you look at this thing, the observation is that so let's do it real quick here. So if you take one of these primes and you multiply it by zeta, the point is this thing is 1 minus p to the minus s times the sum of 1 over n to the s, which equals the sum of 1 over n to the s minus the sum of 1 over p n to the s, n running bigger than or equal to 1, n bigger than or equal to 1. And since these sums are absolutely convergent, and this is just a sub-series of this thing, we clearly see that this is the sum of 1 over n to the s, n bigger than 1, and p doesn't divide n. Okay, so we take all of the n's that are divisible by p. This is exactly what we're doing here. Okay, and excuse me, this should have been bigger than or equal because 1 is not taken out here. But the point here is that if I multiply by a finite product like this and I repeat this process, I see that I should get the sum of 1 over n to the s, n bigger than or equal to 1, where if p divides n, then necessarily p is bigger than big P. So we've taken all the primes less than p, so we must be like that. However, remember we messed up, we missed the 1, so 1 is still not taken, so this is what we have. So this is valid for sigma bigger than 1. And the point is, this finishes it, so there's no need to talk more here. This thing here, it's a tale of a convergent series. So again, it goes to 0 as big P goes to infinity. So you can show that this goes to 0 as big P goes to infinity, which means that this whole thing, what happens to it is that for big enough P, if we choose P big enough, then we can't be 0. This can never be 0. The left-hand side can never be 0 because it's close to 1. So for big enough P, this star is not 0, but none of these factors is 0. So we can divide by them out, and this makes zeta not 0 for sigma bigger than 1. Okay, so this finishes the first important consequence of this Euler product representation. There is yet another important consequence of it, and it's the following. So let's introduce the following. So there's another important connection. So let's say an important connection of course with primes. So let's say another important connections with primes. So as an important consequence of this Euler product representation, we can see that, so let's introduce this function pi of x, which is the number of primes p such that p is less than or equal to x. So this is what pi of x is. And the point here is that we can relate kind of a function of zeta to this p. So if we take log zeta of s, that equals s times the integral from 2 to infinity of pi of x over x times x to the s minus 1 dx for sigma bigger than 1. So let's call this a theorem, I guess. But first things first, I need to tell you what log zeta is. So here, without getting too much into kind of the technicalities, but the thing is, here's what you can do. So here's a proof, but inside the proof we're going to define what log zeta is. So log zeta, you can define it, for example, in this way. You can define it to be ln of zeta of 2 plus the integral from 2 to s of zeta prime of s over zeta of s ds. The point being that since zeta has no zeros and is actually holomorphic to the right of 1, so the point here is that zeta is holomorphic and non-vanishing on this simply connected domain, then it must have a holomorphic log. In particular, we can choose this holomorphic log, and the observation is that if you take log zeta, let's look here, let's look at the product. If you take log zeta for the s, like for a real s, for s over here on this line, we can take the log term by term, and we get, so we can take the log term by term, and we get the sum log of 1 minus p to the minus s. So this is running over the primes. So this is valid for, let's say, real s, because the log here, so let's just point out that log zeta s is ln zeta s for real s bigger than 1. So for real s bigger than 1, this is valid. And how do we see that it's valid everywhere? Well, because both sides are holomorphic and we're in a simply connected domain, so and these sides agree like on a line that has a limit point, and so on by the identity theorem. This holds everywhere. Alternatively, you could take derivatives over here, both sides, and then observe that they agree at 2, at s equals 2. So if you take the derivatives, you see that the derivatives are equal, and then you can observe that thus the functions, the difference of the functions must be a constant, but that constant must be 0 because they agree at at 2, excuse me. So this holds for sigma bigger than 1. And the important observation here is that, here's the observation, here's a very cool observation. If you look at pi of n minus pi over n minus 1, this thing, it can be, it's like, it plays the role of the indicator function of primes. So this is 1 if n is prime, and 0 otherwise. Why is that? Well, that's immediate by the definition. If x is prime, then pi of x minus pi of x minus 1 is pi of p minus pi of p minus 1, but pi of p, which is the number of primes up to p, is 1 plus the number of primes up to p minus 1, minus this thing, pi of p minus 1. So this is 1 when x is p. And when x is a prime, when x is not a prime, it's immediate that when x is not a prime, pi of x is equal to pi of x minus 1. That's clear. So this plays the role of the indicator function of primes, and therefore we can rewrite log zeta of s as if you look at this sum, what we can do is, since this is an indicator function of primes, we can sum over all the integers of pi of n minus pi of n minus 1. Of course, we're gonna run from 2 to infinity now, of this difference times log of 1 minus n to the minus s. Okay, so that's the observation here. And why does that matter? Well, it's because if you think about it, you can easily see that like in the Stiltius sense, let's put it this way. So in the Stiltius sense, if we call this thing g of n, then in the Stiltius sense, this equals the integral from 2 minus to infinity of g of x d pi of x. So if you know a little bit of measure theory, or if you know the Dirac measure, you know that we can write things this way. But if you integrate by parts, you see that this is the integral. So this is, let's see, did we miss a minus here? So yeah, I think we did miss a minus. So if you integrate now by parts, you see that there's going to be a negative coming from the integration by parts, and the boundary values, they disappear. I'm going to show you why, but for the moment, let's observe that this is the integral from 2 to infinity of pi of x g prime of x dx. Okay, but so this is integration by parts. The important observation here is that I mean, apart from the fact that g prime of x is clearly minus s x to the minus s minus 1 over 1 minus x to the minus s. So we have this derivative, and hopefully we didn't do any sign mistake, but the point is this becomes log zeta, thus becomes the s, we can pull it out, and then we're integrating from 2 to infinity pi of x x to the minus s minus 1 over 1 minus x to the minus s dx, and this is exactly what we were looking for. It relates log zeta to the number of primes up to x in this rather surprising identity. Maybe just for completeness purposes, let me note that over here we use the fact that pi of 2 minus is 0 because there are no primes less than 2, strictly less than 2, and the other observation is that we know clearly that, let's see how to put this, pi of x g of x, this is bounded. Let's see what it's bounded by. So pi of x, it's the number of primes up to x, but there can't be more than x because these are all the integers. And then clearly from the definition of g, like if you expand the log, you see that this is up to a constant. This is going to be less than x to the minus sigma, where sigma is the real of s. So this is c times x to the 1 minus sigma, but sigma is bigger than 1, so this goes to 0 as x, as x goes to infinity. So this consequence thus follows immediately. And now we know that log zeta is related to pi of x, which is the number of primes up to x. Okay, so there's one more thing I want to do before I end this video, and I just want to talk about the Möbius function, and then you go. Here's the important thing about it. So here's one more important thing, or one more important connection. So remember, we now introduce the Möbius function. So remember, zeta can be written as the product of 1 minus p to the minus s to the minus 1 for sigma bigger than 1. So 1 over zeta is the product over the primes of 1 minus p to the minus s. And using the same kind of analysis here, actually from now on up to the end of the course, we won't be worrying much about a formal expansion, because you can always do stuff like this, like what we've done here. You can truncate the product and carry out the analysis similarly. But the point is, if you formally expand this product, you see what happens is that when this product is expanded formally, each prime is either chosen or not chosen, right? So from each factor, you either choose the prime or choose one, right? So no prime can be chosen twice. Thus, square-free numbers that are not divisible by a square of a prime. So square-free numbers survive, and numbers divisible by squares disappear, right? Because there can't be any numbers divisible by squares. And thus what happens is that this becomes the sum, n equals 1 to infinity, of 1 over n to the s, but now the coefficient becomes mu of n, and mu of n is going to be minus 1 to the k if n is the product of k distinct primes. So let's say pj, j equals 1 to k, and the pj's are distinct. So if n is square free, meaning it's not divisible by a square, then mu of n, it's minus 1 to the number of prime divisors, and it's 0 otherwise. So maybe you can also say that mu of 1 is 1, just to make it distinct, and then it's 0 otherwise. And is this clear? Of course. If you take like k factors from this product, and you multiply the corresponding primes and you pick up the minuses, you end up with this thing, and otherwise it's going to be 0, because there can't be any non-square free numbers showing up. So this is the Möbius function, and it is connected to the prime number theorem. It's rather another very important function. So let's take an example. Let's compute a few of these. So for example, mu of 30, it is mu of 2 times 3 times 5, for example. These are 3 distinct primes. So this is minus 1 to the 3, and hence this is minus 1. And then let's take another example. Let's say mu of 12, for example. So this is mu of 2 squared times 3. So this is a square dividing 12, and hence it's 0 right away, and so on. You can play with these numbers. So one very important identity about the Möbius function, apart from other things that we'll be discussing later, is the so-called Möbius inversion. So let's quickly talk about that. So Möbius inversion. So it is the fact that if we sum mu of d as we run over the divisors of an integer q, this is going to be 1 if q is 1 and 0 if q is bigger than 1. And you can think of this as an orthogonality property, but we can also think of it as an inversion property after we introduce something called convolution. But for now, let's see, how on earth can we prove something like this? So real quick, here's what happens. So we can observe that 1 equals to zeta of s times 1 over zeta of s. And we know that zeta is this sum. And we know that 1 over zeta is this sum. We just showed that. If you expand this product, you end up with this identity. So if you pick up the coefficients, this is what you're going to have. So these are going to be the coefficients, and then 1 over q to the s. And then it's quite immediate that this is going to be 1 exactly when q is 1, and it's going to be 0 otherwise because of this equality here. So because of the equality of these two, if you compare the coefficients, you see that this follows. Okay? We will see that this is significant actually, and we will see that the Möbius function, it's connected to the pi of x that we've seen above, and we're going to see a statement about something called the prime number theorem concerned with the asymptotics of the primes, the number of primes, but we're going to get to that later. Thanks for watching.